So a very good afternoon to all the esteemed participants and our esteemed resource person. So today in this session 6, we are having Professor Sunandan Baruah sir, and let me take the privilege to introduce Professor Baruah to our participants. So Professor Sunandan Baruah is presently working as a Dean, Engineering and Technology, Assam Downtown University, Gauhati, and CEO of Globino Engineering Solutions, Guwahati, and consultant of technical agency for Spurti project under Ministry of MSME. So he was the previous director in the Center of Excellence in Nanotechnology and professor, Department of Electronics and Communication Engineering, Assam Don Bosco University. He was a research faculty, electron microscopy and nanoelectronics, Angstrom Laboratory at Uppsala University, Sweden. He was a research specialist, Asian Institute of Technology, Thailand. So his research interest is in environmental nanotechnology, and his research concept is to make use of inexpensive weight chemical methods to fabricate innovative materials and device components. His research group is using semiconducting and metallic nanomaterials for applications like water purification, contamination sensing, and remediation, solar energy harvesting, functional building materials, nanopiezoelectronics, etc. So he has more than 250 publications in international peer-reviewed journals and conference publications, 8 book chapters, 3 patents, and 3 invention disclosure forms submitted for verification. So Professor Baruah is a social entrepreneur, and his company Globino Engineering Solution is currently manufacturing nanotechnology-based solar-powered water purifiers and fruit and vegetable dryers targeted for use by rural people. His company also manufactures nanomaterials for laboratory use. So I welcome Professor Baruah for this session, and I now request him to deliver his talk. Sir, please. Sir, I think you are muted, sir.
Okay, all right. Thanks, Manas, and a very warm welcome to this session to all the participants. Good afternoon. And unfortunately, I don't know why, most of the faculty development programs where I have given lectures and also all the workshops, I'll say 95% of them, the sessions given to me are the post-lunch sessions. I don't know why the organizers have, it's very difficult to keep the people awake, but I'll try my level best. I hope all of you had your lunch. And online it is even more difficult because I don't get to see you guys. But anyway, first of all, let me apologize. I don't really have a structured presentation for today. Unfortunately, there was some issue that happened early morning because my plan was to sit today in the office and prepare the presentation. But unfortunately, one of my uncle and auntie, they were murdered today, very early morning, by some miscreants who came to, they looted their house. And, unfortunately also the caretaker of the two happened to be my driver also. So you can understand the situation since 7 in the morning today, it's like police and everything. So even now in office, I'm getting constant calls. So I just couldn't get down to sit and prepare the presentation. But anyway,
yes, sir.
So we'll still have the discussion, and I did put in certain slides yesterday night. So let me try to share my presentation. All right, before I go to the presentation, Manas, from you, this FDP is all about quantum computing, isn't it?
Yes, sir.
So most of the sessions are on quantum computing.
Yeah.
So definitely, today is which day? How many days till now?
Today is the second day, sir.
So you already had 2 sessions, 3 sessions, I guess, no?
Yeah, per day 3 sessions. So 2 sessions are completed for this day.
Okay. All right. So you already are aware of a little bit about computers that we are talking about in the form of that follows quantum physics, quantum mechanics, quantum confinement, right? So I will not lay too much of stress on the computing part because I've been given the responsibility to discuss with you about the possibilities or about the role that is played by nanotechnology in developing these futuristic computing systems. And honestly, if you look at it, or if you understand how quantum computers can actually be brought into existence, can actually be available commercially, this can happen only through the inclusion of nanotechnology. There is actually no way out. Okay. Now, I understand from Manas that you are a mixed group of people from various disciplines, and I'm not very sure how much or how many of you actually know how much of nanotechnology. So I will try to give you a quick gist of the basics of nanotechnology and try to relate that to quantum computing and the computers of the future. Okay? All right, before I go to the slides that I put in a few slides. Okay, let me look in case you, because of technical error, sometimes it's very difficult to understand. So in case you do not hear my voice, sometimes just stop me, or you want to ask something, just stop me, okay? Because Manas is given a 2-hour session, it's it's quite long, but we will move gradually. I'll just try to see that you guys are awake, and we can share some amount of information as far as nanotechnology is concerned. Now, just to give you a feeling of the possibilities through nanotechnology, I will start with a small video. Hopefully, I will be able to share it, and hopefully, you guys will be able to see it. Because for me, giving presentations, some hiccup always comes up, technical hiccups. Okay, so let me try that. I remember every time I used to give presentations after returning to India, my laptop used to give issues because it's an Apple laptop, and there's always problem with the projector. Okay, I think Manas will also remember there many times in Gauhati University we got stuck. So those might happen. So let me first try to start off with a video. This is on. This is actually made by Cambridge University, and it's quite an old video. And I love to show this video because it shows the tremendous possibilities of nanomaterials, of nanotechnology, and also because my research group, the group members are involved in very similar research. Now think about your cell phone. Okay, let me. I think use the correct word will be smartphone. You guys all have smartphones now. Not you only. Everybody has smartphones now. Even the vegetable vendor also uses smartphones now, right? And I don't know. Some of you may have been lucky like me. Some of you may, but I'm sure all of you are very young people. So I had gone through that complete phase-wise transformation from no telephones to wired telephones to mobile phones to smartphones. Okay, and believe me, this transformation is tremendous. And even now, young generation, they're not happy. My son is never happy. He's never happy with his smartphone. There's always something or the other that irritates him, and he says it's time to go for another one. So what are your expectations from your phone? Are you happy with what the phone is delivering to you at the moment? Or you want more? And if you want more, what more do you want? well, the possibilities are immense. You can even, difficult to visualize also that so many things might be possible. I'm giving a very simple example through this video. Let me try to share the video. Hopefully it will play. Okay, let me just go to share tab. All right, so let's see. Okay, Manoj, you have to tell me, can you see it?
Screen is shared, sir. So now I
Okay,
think
the video is playing.
yes, sir.
Okay, so let me stop sharing them. Okay, so all of you could see that video, right?
Hi guys. What do we know about cheetahs? Many of you probably know that cheetahs are predators of the family Felidae, native to most countries in Africa and the Middle East. They are also the fastest of all land animals.
Okay, sorry, the video was still playing. Now you can hear me, right? Someone?
Yes, sir. Yes, sir.
Okay, let me switch off my video. It will save on the bandwidth. Okay, so you see the possibilities. That's just a very simple. Actually, it's, like I told you, it's quite an old video. But all these things are actually done. Okay, all these things are very much done. And in fact, my own group has been doing very similar work. So, nanotechnology, why it is becoming so interesting or exciting, is not because it is brand new or it is something very, very new. It's not. Nanomaterials people have been using for thousands of years, to be honest. Okay? But what has become exciting is the instrumentation development that has happened over the last 2 or 3 decades that has allowed us to play around with atoms. And when I say atoms, playing around with atoms, I literally mean it. You can actually make your own materials now. I remember giving a lecture somewhere in, I think it was in the University of California, and there was this bright young student, because I was talking about novel materials, about new materials, and he asked me, "So, sir, you are trying to add something more to the periodic table, right?" Well, I had to explain to him that it's not a new element that I'm talking about. It's a new material. So we are so used to identifying material with the elemental composition that, when it's a new material, we immediately think about the atomic composition. We think about the atomic number, and automatically that little guy, I won't say little, he was an undergraduate student. So he thought that maybe I'm trying to put in a new element in the periodic, and he was literally asking me, where will you put it? It's already filled up. Well, that is the answer. That what I mean when I'm saying that we can actually make our own material, I mean is that you can actually pick up atoms and place them where you want in a particular matrix. So, I can come up with a material that has a few layers of maybe one type of atom, another few layers of a different type of atom, again maybe repeat it. All these possibilities are there, and this is something so unnatural. When human being has the power now to actually do this, and this has given us a lot more power as far as developing new systems are concerned, and so ample possibilities are there. We can dream now, and we can dream, and we can try to achieve these dreams. All right, now let me move over to the slides and see if we can move in a more structured way. But just wanted to give you a gist or a feeling of the need for or the importance of nanotechnology. All right, let me share my screen again. Can someone confirm you can see the screen or not?
It is visible, sir.
Okay. Anyway, you see, very simply, I just had to put in. I just wrote the title now before I joined your program because of lack of time. Sorry. Anyway, start with two questions. Okay. What is quantum computing? You already know it. So, a new paradigm for information processing, astounding speed. So, we actually like all the functionalities that we want in our cell phone, because nowadays people are more you can say obsessed with the cell phones rather than the laptops, right? And cell phones have almost nearly replaced your laptops. However, of course, if we talk about some sophisticated softwares and all those might be difficult, programming might be difficult, but otherwise, for regular use, the phone is much more easier than the laptop. So anyway, we expect to do a lot of things and we want to do it quickly. Gone are the days, if you remember, when you used to download a video or watch a video live, there was this buffering going on. There's this circle rotating, and you get upset. Well, I don't see that anymore now. It hardly happens unless unless it's in a very poor network area. Things are happening very fast. How is it happening very fast? It's because of the concept of parallel processing. So we do not have one single processor now. We have multiple processors working on it, and any instruction is divided. The work to be done is divided. It's like previously I was doing the work alone. Now I have 4 or 5 people working with me, and that's why we can be faster. As simple as that. Well, not so really true, but then it's not as simple as that. But of course, we have that, right? We have quad processors, then we can use octa processors, hex processors. Okay, so many processors working in tandem. Working in tandem means they are governed by single clock, all right? Because we're talking about very high speed. These processors are capable of, executing 1 million instructions per second, maybe. Per second, okay? That's million instructions per second. And we may have 16 of those processors sitting in your cell phone and doing it. So it's literally like if one can handle 1 million, then 16 can handle 16 million. So you can think about it, maybe 16 million instructions are being processed every second. That's huge. Literally huge. And even then we are not happy. The consumers are not happy. We need more speed. We need more activities happening on the cell phone. Now, how is this actually possible? Okay, that is something we have to reflect on. So typically, if you say what does nanotechnology have to do with quantum computing or quantum computers or quantum computing systems? Well, it will be almost everything. Okay. So even don't really have one to show you immediately this is a quantum computer, but you can understand what I just mentioned about parallel processing. Quantum computers will be able to handle that, that amount of load using a single processing unit. Okay, that means what takes maybe hours at the moment can be done in seconds if you can actually physically get the quantum computer working. Okay, so it's very similar to like quantum computer to your laptop is more like laptop to the abacus. So you can think about that abacus. Even we did not use as kids. Forget about you guys. Now, if you look around, almost all the big players, very big companies, governments, are investing a lot on the developing quantum computers. So they want to study deeply quantum information. But why? Well, quantum computers, if made, they'll be able to solve problems that are impossible to solve with ordinary classical computers. Impossible not because we don't know how to solve it, impossible because of the processing time. If you want to solve a problem and your processing speed allows you to solve in 1 year, then it's not worth it. And it's difficult also. It happens. Many of my students who are using, simulations, they keep complaining, they started, but, it just couldn't complete it. It's just going on and on. I need a better computer. We need a much higher speed. You need extra RAM, all of those. So the problem that we have there, so we are upset, right? So we need a solution to that. That is possible, actually, and bringing it down to maybe a few seconds. So quantum processing allows measurements to be made at the limit set by the quantum mechanics. Okay, so I'm sure all of you being faculty members, you are definitely conscious about the fact that when we decrease the size of something very, very small, we go smaller and smaller and smaller. The classical physics, classical mechanics doesn't hold good. And then we have different phenomena happening, and we need different set of equations to govern the activities of the same material with reduced size. A simple example I'll tell you, gold is golden in color in the bulk, and gold is anything between red to black, red, blue, purple at the nanoscale. Similarly, silver also can be anything from blue to green to yellow. We have made that in our labs, ourselves. In my own lab, we are making silver of so many different colors. So why is this happening? Okay, because there is a change in the optical property. Quantum communication offers security. So now you know about security issues now. More we are using the internet, more problems we are having, more number of cases of cheating, more number of cases of blackmailing, so many things happening. And that means even after so much of security studies, big books being written, cryptography, so many different ways of securing your data. Even now, a lot of unwanted activities are happening on the net, which we cannot avoid. But with quantum communication, this is possible because of the high processing speed. Okay, things can be made so fast that I think, of course, humans are smarter because they are anyway making everything, so they will also find their way of hacking everything. So let's see. Well, a big problems that is given as a typical example. You might have already have come across this. I won't go into details of that, but just to give you a feeling. Factoring is in mathematics. It's a very, very time-consuming process if you have to do it for big numbers. So may take a lot of time. But with a quantum computer, quantum processing, quantum computing, we can bring it down. It's like some factoring may even take 1,000 years, which can be done in a few minutes maybe if the quantum computer materializes. Okay, conceptually this is done, it is possible. So if you're talking about the hardware part now, so computer chips are filled with gates, right? If you know or have some basic knowledge on electronics, of course, gates are again composed of transistors. Okay, so these are digital circuits, digital components, discrete in the sense of its own performance, but if you look into it, these are actually made out with transistors. And with the reduction in the size of the transistors, everything is becoming smaller and smaller. The integrated circuits now are extremely small. And at the same time, the number of transistors is also increasing. We are not, moving away from Moore's law. You all know about Moore's law, right? Roughly, you can say that, the transistors on a particular integrated circuit or surface area of silicon will double almost every 1.5 years. That means today I have 1 million. After 1.5 years, I'll have 2 million transistors on the same area on the chip. And we have not yet gone for multi-level active components as yet, believe me. We talk about multi-level chips, but when you talk about the active components, that means the transistors, they're still on one single level. The other levels are used for interconnecting. And transistors have become so small now. That we are almost at the position of you can say going beyond solid state transistors. Just hold on, please. Okay. It's happening fixed video. Accordingly, we'll see which expert is available. Okay. Okay. Sorry about that. So, the transistor size is getting smaller and smaller and smaller. And, Intel is a company I simply love because this company is actually making all these impossible things happen. Okay. So, even in, we can say integrated chip design, integrated circuit manufacturing, we have gone out from the you can say realm of microelectronics to nanoelectronics now. So there also, when you're talking about nano, we are basically talking about nanotechnology. So nanotechnology is governing the way electronic systems are behaving, the way the miniaturization is happening, the way the clocking is being applied. So you can think about it, just to give you a rough idea to those who are not really from electronics or know much of electronics. Currently, if you talk about the transistors that we are using in integrated circuits, if you take a piece, cut off your hair and you look at it from the tip, the width or the surface area that you see at the tip, not the length, okay, on the surface of the tip, this will be able to accommodate maybe a few billion transistors interconnected with wires. So can you visualize what we are talking about? Well, that is nanotechnology. And the way things are going, that means, because you see, we are taking the transistor down and down and down. And if you know that transistor operates, it's all about the movement of electrons through some channels by applying certain voltages. And we can control the movement using certain other voltages in certain other parts of the circuit. Like we apply for a field effect transistors, we apply a voltage at the gate and we control the movement of the electrons through a channel. So all these voltages are there and transistors are becoming smaller and smaller and smaller. A lot of issues are coming up as far as the electrons can actually just move from in different directions where they're not supposed to move because the thickness is so less. The concept what we call as tunneling. So tunneling means actually moving through something, or it's moving through an obstruction, making a hole instead of climbing on top, making a hole and going in. That's tunneling. And that's happening in the electronic scenario. So gates will now move to the atomic level. Okay, so we are talking about single atoms now. Previously, we had transistors where the gate will be maybe about a few 100 nanometers, the source and the drain a few 100 nanometers, okay, and then we used to apply some voltage. Now we are going down and down and down in size. Intel now making about 6 nanometer size transistors. Okay, when you say size of a transistor, you mean if you consider it as a square, the side of a square. Okay, it's going down to about 6 nanometers. 14 nanometer already commercially done. It is included in the processors. Okay, and that's why obviously when things are going smaller and smaller, the processor is also going smaller and smaller. Okay, but the quick question here, can one of you tell me, if the things are going so smaller and smaller and smaller, why are our cell phones not becoming smaller and smaller and smaller and smaller? Why are they still stuck to that typical type of a size? Can somebody tell me why? Conceptually or theoretically, we can have the cell phone inside the ear. We can just put it as a small earbud. And that can do everything if you talk about the processors, the amount of silicon area. But even then, we make a big phone. Why? If you open up your phone, somebody wants to say? Okay, the answer is in your hands actually. If you open up your phone, and look inside, you will see the huge battery. Battery is what is occupying the space. Battery technology is not moving at the same speed as the integrated circuit technology. And that's a problem because we want more and more power because so many processors working together, so many apps working parallelly. And that's why nowadays your phone, you need to charge maybe once, twice a day sometimes, right? Because the battery is not able to handle. That's why the decrease in size is not happening there. So battery something will be there. So, but when you're talking about quantum computers, we are not talking about making the computer smaller and smaller and smaller. We are talking about increasing the processing speed. Okay, doing things which appear impossible at the moment as far as computation is concerned. So, your quantum computers, theoretical things are almost done, experiments are on process, actual fabrication may take some time. But you can well expect something happening within a decade. Okay? These I'll not discuss much because I think you are already discussing that. That is going more into the structure of a quantum computer. I'm not going into it because I'm talking more on the nanotechnology involvement in quantum computers. But basically, you can think about a typical computer now, the processor. We refer to the digit as a binary digit because it follows binary algebra. So it's like binary digit condensed to bit, and it can have two states, 0 and 1. Whereas the quantum computers will say quantum bits or qubits. Okay, and there's a huge difference between a bit and a qubit. So if you just look to compare the storing capability, then n bits can store 1 of 2 to the power of possible n possible numbers at any time. Okay, n qubits can store all at once. Okay, 2 to the power of n numbers. If you have n bits and your word length is n, okay, you can have one at a time. loaded. Whereas this one parallelly can load all of them to the power n times. Okay, so that's the speed. So ultimately, as the processor speed increases, we need more and more storage, because of these intermediate results coming in, we need to store somewhere. We need to store, pick up again, store, pick up again, store. It goes that way, right? So we need more. That's why we say more RAM, right? So it will increase exponentially. Okay. So I won't discuss all these now, but just to give you a feeling that the processing speed will increase exponentially when we go to quantum computers, and instead of bit, we use qubit. And solving complex problems will be easier. Let me avoid all this. Let me go more towards the nano part. So a lot of possibilities of quantum computing, a lot of applications that is doable. You can model very, very complex systems. Okay, human systems, we are still yet to properly comprehend them. Simulation is sort of like a out of the thought at the moment, but we can do it. The possibilities can be seen in quantum computing. Even books are coming out, okay, nowadays, because physicists has really taken this very seriously. So you get the science fiction. This book, I haven't read it as yet. Hope to read it soon. Okay, so science fiction writers are taking the fancy of quantum computing. I want to introduce you guys to this particular gentleman. I'm sure many of you know him, but if you don't, he is Sir Richard Feynman. And for nanotechnologists, he is the father of nanotechnology. He is the first person who sort of hinted at the possibility of working at the nanoscale, with the possibility of manipulating matter, the possibility of writing the complete Encyclopedia Britannica on the tip of a pin. But that too at a time when this looks like science fiction. So he a Nobel laureate in physics. In 1959, he gave a beautiful lecture where he said that there's plenty of room at the bottom. And all nanotechnologists will definitely mention him, because he showed the pathways, he showed the possibility of the development of nanomaterials. Now, he also gave a wonderful talk on the possibility of quantum computers in 1981 at the Massachusetts Institute of Technology. Okay, there's a conference on physics and computation, and he was talking about quantum computers there in 1981. So this is what he said. Is it possible to build computers that uses the laws of quantum mechanics to compute? Okay. So now the answer is definitely yes. So we are discussing about quantum computing. What exactly do you mean when you say quantum computer? Well, basically computer that uses quantum mechanical phenomena to perform operations on data through devices such as superposition and entanglement. These are new terms coming into, new terminologies coming into electronic systems design. Okay, so instead of the bit, you are talking about the qubit, and the qubit will talk about superposition and entanglement. So it's a whole lot different from the classical computer that we use at the moment. So just a minute, please. Okay. So now we are talking about data manipulation, data storing at the atomic level. Okay, so we can have consider the spins of the electron, because electrons spin in two different directions. Not all. I mean, say if one rotates in one direction, another may rotate in the other direction, and we can actually use them to designate different energy levels. The best thing is that in qubit we can use the energy level of the atom, not the electron. Okay, and that gives a higher energy level that we can work on. And some other implementation possibilities. I won't go into details of these. Okay, polarization of a photon or NMR. Okay, that will again take a lot of time to discuss at the moment. Roughly, you can say, I was saying, no, maybe in a decade time we start with our quantum computers, and of course within 100 years it will be boring. So, a lot of things which is not possible at the moment will be possible once the quantum computers are in place. Now, I just pull in some of my slides from here and there hurriedly. So I'll definitely give you an intro to nanotechnology, but right now, of course, already I think you are going to you're having an idea of what we're talking about. So we're talking about things that are extremely small. And how small is small? It's a very relative term. For us, this range of size that we're going to work with in nanotechnology, though it's not rigid, but in general, people like to give a definition that we work in materials in a size range which is less than 100 nanometers in at least one of the three dimensions. Okay, so any material will have three dimensions. So any of the dimension, it may be 1, 2, 3, all of them in the range of less than 100 nanometers. And in that size range, things behave differently. All right, now you can stop me anytime. Okay, so just to me being a nanotechnologist, I would love to make this position very clear to all of you that nanotechnology, the need for nanotechnology, the importance of nanotechnology, why we need that. Now, if you simply look at the case of the decrease in size of the electronic circuits, the integrated circuits, you're talking about following the Moore's law. Okay, so the number of transistors on an integrated circuit keeps on increasing, and it's going on. So microelectronics had done that. That means the processes developed by Intel. Okay, that's why I love Intel. They actually not only started just doing things, they started exploring, they started doing a lot of research and development, and they came up with unique theoretical concepts on the microelectronic processes like ion implantation or oxidation, metallization. All these processes they systematically studied, and that's why it was possible for them to go on miniaturizing. So microelectronics made an impact only in the electronics field, only in the integrated circuit field. And that's why we don't refer to it as technology. We don't say microtechnology. We say microelectronics. But we are not saying nanoelectronics, we are saying nanotechnology. Nanoelectronics definitely is a branch of nanotechnology, but nanotechnology, we use the term technology because it makes, or it has made an impact in all vertical sectors, in all possible areas. Okay, and that's why many people prefer to call this as the next industrial revolution. You remember the Renaissance happening in Europe when machines were introduced in the factories. Many people lost their lives, but that's about a huge transformation in the way production was carried out. Okay, so that was what we call the Renaissance. And similarly, many people try to say that nanotechnology is a renaissance that is making an impact in all the areas of science and technology. Anyway, so you see, these everything works with tools. We have tools, we can do things. We have machines, we can do things. Okay, so just showing two tools from the medieval age and the modern age. Okay, this modern age machine I had played around with a lot when I was working in Europe. Okay, so that's a typical Transistor electron microscope. Okay, now when nanotechnology came in, there were no experts. Obviously, there were no experts, right? And many people were very skeptical. They were not very sure whether this is something we want or not. Of course, many experts in various domains, they already use, or they are comfortable with the traditional way of doing things, and they didn't want to come over for a change. They were not comfortable. They said, no, this is not done, this is not happening, these are bogus results, this is not correct. How is it possible? Because they are not adapted to using that technology. But gradually, of course, people are moving into it, and anything happens, initially there's some protest going on. People try to point out some negative aspects for everything, but we need to go on with that. We need to be careful about the negative aspects, of course, but just thinking about it and avoiding any advancement is not, of course, what we want to do. So actually, this is the speech I was talking about when Sir Richard Feynman said there's plenty of room at the bottom. So he was talking about things so small. Now, just to give you a feeling of 1 nanometer, that's roughly 3.5 gold atoms. Okay, that is 1 nanometer. And you see the long tube, the big tube, that is a hair, and below that we call what is nanofiber. So typically hair is about 50 to 100 micrometers in diameter, and these nanofibers can be anywhere between around 5 to 100 nanometers. Okay, so very small, and that is the scale we are talking about. Okay, how many of you are awake? I've been talking for quite some time now. All right. So let me just continue a few more minutes, and then we'll shift to some other topic. So basically, the term nanotechnology, even though the concept was put forward by Sir Richard Feynman and one of his PhD students, Eric Drexler, he promoted the whole concepts. He even wrote a book called Engines of Creation, where he talked about nanorobots, nanomotors, nano working systems, mechanical systems. We now actually have nanorobots working. Okay, and that's a different concept, of course. We'll talk about it sometime later. But basically, it's the typical, egg and hen problem. Some say, okay, nanotechnology resulted from nanoscience, nanoscience resulted from nanotechnology. Okay, no, it's a circle that goes on, but they are together always. So nanotechnology is simply the implementation of nanoscience. Okay, and you can take it to various, what you can say, ways of looking at nano. Okay, some might say that this is a new integrated technology. Some will say it's just an hype, an overhyped word. Because if you remember, the first nano commercial products were launched by Samsung, and they said our nano series of products. They had washing machines and microwave ovens, OTGs, and all of those, where they said they use nanotechnology. Well, they only used a layer of nanoparticles of silver, which gives very strong antimicrobial properties. And that's why they said that we have used nanotechnology and our systems are very, very sophisticated. Well, there's not much of sophistication in that. There's simply, overhyping some technology and trying to squeeze in some money out from the customers. Well, it has become an area of study also now. Many universities are offering programs in nanotechnology. Okay. it is a platform for development for various verticals. Okay, it's an interdisciplinary science, very much an interdisciplinary science, because as you know, like I said, nanotechnology or nanomaterials that we are making now, because or with the assistance of certain machineries, nature has been doing that for millions of years, rather billions of years. And nature does not use those machines. I have never seen any machine being used by nature. Not very sophisticated conditions. It's mostly temperature and pressure variations, not too much of high pressure, okay, a few atmospheres at the most, okay, and that's where nano materials are being made by nature. And what we need to do is we need to mimic nature. We need to try to understand what nature has been doing or is still doing, and we try to do it or replicate it. Okay, that's what I do, and I always considered Mother Nature as my teacher in nanotechnology. Anyway, this is all about size, okay, and gradually with technology we are going down in size, and we are actually at the level of molecules now. Okay, so we have gone in size of physical dimension to almost at the molecular level. Okay, and a lot of things are happening now. Just to build up the case on the motivation part, why nanotechnology? Well, it's that again, vicious circle. We say that we are talking about global warming. Things, it's very hot, and one cause we blame the air conditioning units to be responsible a lot for the reduction of the ozone layer that allows ultraviolet light to come in and the infrared radiations to come in and make life difficult for us. So, but what is happening now? 10 years back, the number of air-conditioned cars and the number of air-conditioned cars now, it's a huge difference. Now I don't think any car comes without an air conditioner. Why? Because it's so hot. And you have every justification, every right to say we need air conditioners because it's very hot. But if you're asked, why is it very hot? You'll say, because we are using a lot of air conditioning, right? So it's a difficult circle, you cannot come out of it, okay? You cannot come out of it, and this global warming is happening, all right? So we are living on a hotter and hotter world, okay? We are using up our fuel, okay? Fossil fuel being gone, that adds a lot of pollution, okay? So a lot of negative things happening when we are making our lives comfortable, okay? We need all of those. We cannot think of saying that we stop the cars and we start walking. We cannot do that. In fact, every household now has maybe at least 2 cars, right? So a lot of these happening, pollution, smoke, smoke and fog. Now they have a new term called smog, which is a new entry into the dictionary. That is smoke and fog together, right? So situations like this, okay, where you don't see anything, this is not fog, this is smog. Okay, this is also smog, okay? One in the US, the other one in China, okay? So what is the need of the hour now? We need a non-destructive technology, okay? Environment-friendly technology. And most of the scientists believe, I personally also believe, that nanotechnology may be a solution. It can be considered as an environment-friendly technology, only that we need to be very careful when we use it, okay? So this can be the solution, okay? Manas, I have till 4:30, right?
Yes, sir.
That means another 1 hour. Okay, fine.
You can take your time, sir.
I mean, I will maybe stop a little bit ahead of that. And of course, you can have a lot of discussions on. But anyway, just to give you a brief on nanotechnology. Well, the term nanotechnology was coined in 1974 by a Japanese scientist called Norio Taniguchi, actually, to be correct. And it was popularized by Drexler, who is a doctoral student of Sir Richard Feynman. So we talk about dimensions below 100 nanometers in any of the 3 dimensions. And 1 nanometer is 1 billion of a meter, and there will be novel properties at the nanoscale, okay? And I'll quickly tell you that we can make nanostructures in 2 ways. We can break a big bulk material and break it down to the size we want, which is extremely difficult. We cannot do it with a hammer. because the hammer roughness is in micrometers, and we are talking about small 5 nanometer, 10 nanometer particles. A hammer can never break a material to that size. For breaking it, we need very, very sophisticated instruments, lithography instruments, right? Electron beam lithography, ion beam lithography, maybe, and a lot of other high-end processes, very, very expensive processes. You can do that. Otherwise, you can go for simple term or simple process. We call it the bottom-up process, where we can start with individual atoms, and we add up the atoms and get to the size we want. Okay, and then we stop the process. Okay, it's not difficult. It can be done chemically, very easily done, and that's why most of the senior nanotechnologies that you will find in today's world, they come from chemistry background. Because initially when we started it, of course, a few rich labs could manage to procure the instruments. In fact, the first transmission electron microscope that was ever made in this world by Germany is still kept as a decoration piece in the lab I was working in Sweden, in the Angstrom laboratory. They had put it there. Well, Germany actually made that machine for the US. But this was during the World War II, and of course, Germany will in no way ready to give to US, and Sweden quietly brought it and kept it in Sweden. Okay, so I was lucky to have seen it and have taken photograph with it. Okay, it was just there at the entrance of the Angstrom laboratory in Uppsala. Anyway, so not all the labs had these sophisticated facilities, but scientists quickly found out that we can actually go the bottom-up process, where we can start with individual atoms. We can separate out the atoms and create conditions to bring the atoms together, and that does not need sophisticated instruments. And it was very common for the chemists to do this, because they play around with atoms. They know the way it should be done. And that's why most of the nanotechnology labs that started research in smaller universities were led by people from chemistry. So, this is how we actually make nanoparticles in a solvent. Okay, we regularly do it in our lab here. Okay, we start out with atoms, gradually make them bigger and bigger, go through a process of nucleation, then they become bigger and bigger by joining, and the process is called Ostwald ripening. Okay, and they keep on adding up, right? So that way we can keep on making different nanostructures. And let me take a break here from my talking. So let me tell you another story here. I'll again come back to this. So let me first unshare the screen. I'll come back again when we after some time. Let me take a small break. All right. So you guys are still there with me, right?
Yes, sir.
All right. So I managed to remove my screen. All right. So the story is like this. Well, my background is in microelectronics. So I have been teaching, integrated circuit fabrication, microelectronics techniques, and all those I've been teaching in the classes, and always fascinated what Intel has been doing with time. And then they were making, or they were revealing, smaller and smaller transistors. And this question we used to always discuss in class as to how much more can we go in size? Because like I said before, that when we're making things smaller and smaller, the separation between the different electrodes or the transistors also become smaller and smaller. And that's why, sometimes it gets difficult for them to work, because electrons will just tunnel through because of the high electric field. Because even if you put a 1 volt, if the spacing is in nanometers, the electric field is in kilovolts. Okay, extremely high. And that's why we have a lot of what we call as hot electrons forming, and these hot electrons are destructive for the integrated circuits or the transistors as such. So we were wondering what's going to happen next. And Intel was going on announcing smaller and smaller transistors. Then all of a sudden, Intel announced a new type of transistor, and they call it as a tri-gated transistor. And we were at our wits' end as to what exactly is a tri-gated transistor. No books talk about it. There's no information available. So I was wondering, what are they talking about? Are they going to use 3 gates? In a typical transistor, we have 1 gate, right, where we put the control voltage. So are they using 3 gates, or what is happening? And the first tri-gated transistor that Intel announced was a 22 nanometer transistor. Prior to that, transistors were 45 nanometers. And Intel brought it down directly to half of it, 22 nanometers. And it was so amazing to think about how is it possible, such a small transistor, just 22 nanometers by 22 nanometers. How does it work? Or where exactly, or what is the technology? How can it happen? Anyway, I was searching a lot, couldn't find anything. Then I went into the Intel's own website. And there I found a small report by Mark Bohr, who is the R&D head, okay, he's the technical head of Intel, where he briefly described the tri-gated transistor. And of course, it was more like a blog option, and I could write there. So the comment could be put in, and I said, please, Mark, we need a video to know exactly the whole process. I just wrote. I did not expect that it will be seen. And I also don't know if it is because I wrote, but very soon, Intel put up a small video on the working of the tri-gated transistor. So it's all about nanotechnology now, okay? It's all about nanotechnology in electronics. It's all about nanotechnology in building up computer devices, in building up processors. So just to break the monotony, because you have been listening to me for quite some time, let me show you a video, that particular video that Mark Bohr made and put it up on their website. Later it was available on YouTube also. You can find it. The description of the 22 nanometer transistor, how actually, we are trying to modify the transistor to handle the current, because we need currents to drive so many other transistors. Okay, so current has to be high. But if you keep on making it smaller and smaller, the current cannot move. There's not enough, the resistance goes high and not many electrons can pass through. So how do you load, or how do you handle the loading capacity? So again, I'll show you a small video by Mark Bohr so that you guys can wake up. Just a minute, let me share the video. You go through it, then we will discuss.
Hello, I'm Mark Bohr, a senior fellow here at Intel. Most people know Intel as a manufacturer of microprocessor chips. What they may not know is that each and every modern microprocessor is made up of millions or even billions of tiny electrical components called transistors. Over time, transistors have been getting smaller and smaller in accordance with Moore's law. Because of this, computing and communication devices continue to get smarter, faster, and more efficient. Keeping up with Moore's law has never been exactly easy. For 22 nanometers, it became clear early on that continued shrinking was not going to give us the benefits we have come to expect without some radical redesign. I'm proud to say, after a decade of research, we've invented the solution. For the first time in history, the transistor has officially entered the third dimension. What exactly does a 3D transistor look like? Well, I'd love to show you. And in fact, there are more than 1 billion transistors on this single chip. Unfortunately, they are far too small to be seen with the naked eye, which means there's only one way to do this. Mr. Director, I'm ready for my cursor. Okay, so now I'm 20,000 times smaller. And just to give you some point of reference, this huge object off to my right, that's the chip I just dropped. And this large, unidentifiable object off to my left, that's a human hair, approximately 100,000 nanometers in diameter. Believe it or not, I'm still far too large compared to a 22 nanometer transistor to give you a meaningful demonstration. So, here we go again. Okay, that's better. I'm now approximately 100 nanometers tall, or about 20 million times smaller than my actual size. At this scale, a human red blood cell would be about as tall as a 5-story building, and I would be just the right size to demonstrate some of the attributes and functions of a single modern transistor, like this one. For the last 4 decades, planar or 2D transistors have been at the core of transistor design and architecture. Here, we see a form of silicon that creates a stream through which electrons flow. The gate, which is made of metal over a high-K insulator, controls the flow of electricity in that stream. It acts as an ordinary switch, turning flow on and off. That is, if an ordinary switch had the ability to turn itself on and off over 100 billion times a second. Some key objectives in transistor design are to have as much current flowing as possible when in the on state for performance, to have as close to zero current flowing when it is in the off state to minimize power usage, and to switch very quickly between the two states, again for performance. As transistors get ever smaller, one way to achieve this is to get tighter control by having the gate wrap around the channel as much as possible. This is Intel's new 3D transistor. With the 3D transistor's architecture, we replace the flat two-dimensional stream with one or more three-dimensional fins. The control is on all 3 sides of each fin, rather than just one, as in the planar transistor. We call this a tri-gate transistor, and its real advantage over planar is the ability to operate at lower voltage with lower leakage, providing an unprecedented combination of improved performance and energy efficiency. This breakthrough invention allows Intel to create transistors that are smaller, faster, and use less power than ever before, enabling a new generation of computing technology in every category, from the fastest supercomputers to the smallest handheld devices. So, that about wraps it up. All that's left is to just reverse the polarity and the shrink ray to bring me back to my normal size. Oh boy, that's going to be a long walk home.
Okay, let me stop sharing it and okay, so thank you. All right, so you saw how a modification needed to be done to handle the current load, okay? Because
data at an unprecedented rate, faster than our ability to analyze and understand it. To move, store, and compute all of this data requires incredible processing power. From the blazing speeds of our devices to blazing trails within AI, Intel builds chips that are at the heart of nearly everything. Within every Intel chip manufacturing facility across the globe, innovators are pushing the limits of science and literally rearranging atoms to create groundbreaking technology. This strong silicon.
sorry about it. I know my video was still playing. Well, anyway, the new design had to be pulled in, okay? And to handle the load, the current, because typically, because you are making it smaller, two-dimensional, gate will not be able to handle it, okay? Because the channel length becomes very, very narrow. So they increase the channel length by making it into a three-dimensional channel, and obviously a three-dimensional gate. And that's why it comes to be tri-gated. Tri actually comes from the three dimension. Now the problem of going down and down is that, yeah, we know how to do it maybe, But think about it. I have personally worked in, fabs, where they make integrated circuits. A typical fab, you may have to invest about maybe 10 or even more, $100 billion to set up the whole fab. Even the maintenance, the annual maintenance goes to a few $1,000,000. We have other technologies that we can adopt to scale down further. But think about the investment. Who's going to do it? Say, I still remember, my mother making cakes in pressure cookers. I mean, many people still do. That's a different thing. But I remember my mother making cake in pressure cooker, because even though the other technologies like OTGs were there, they're slightly beyond reach, slightly expensive for us, and obviously we would prefer to use the same gas burner and make the cake if we can afford to do it. I mean, if it is possible to do it, instead of investing more in the OTG. Something very similar here. So we have the microelectronic platform already. All the instruments are there. All the processings have been beautifully studied. Everything is in place. So we try to extend it to as much as humanly possible, right? We don't want to set up a new facility spending another 100 or 200 crores, or sorry, $200 billion. So we keep on trying with whatever facilities we have, okay? And that's what actually Intel is doing. So if you see in the video, Mark Bohr, he used, just to make himself small, just to explain the transistor, he gave a feeling that there was a machine that makes him small, okay? And then, when he had that radiation on him, he became smaller. And unfortunately, the machine broke down, right? And he could not come back to the original size. So that was the first video that was put up. And, I showed this video to my students the moment I got this. And I told them, and I asked them, why do you think Mark Bohr did not come back to the original size? There's something in it. Why didn't he come back to the original size? And one student was very prompt to reply, and he said, I think he's going to tell us something more very soon. I said, I also think so. I mean, there is something still there that he has not told us. And that's why he wanted to prefer to remain in the same size range. And very true, within just a month or so, they came up and put up a video, again, minimizing the size to 14 nanometers. Just now, they were explaining the concept of the 22 nanometer transistor, where they made a three-dimensional channel with a three-dimensional gate. And then all of a sudden, they say we can even do it at 22 nanometers. That's even we can do it at 14 nanometers. That's roughly almost a half of what they were talking about. And again, the question, was how do they handle the load? Because they made it even smaller now. So will that same tri-gated transistor deliver the same amount of current, or will there be something new in it? Okay. So if you are not bored, I'll show you the second video also on how they actually went down. These are all nanotechnology techniques, okay? How they can even modify the design to handle the same amount of current as the 22 nanometer transistor, okay? So let me quickly show you that video, the other video.
So that about wraps it up. All that's left is to just reverse the polarity on the shrink ray to bring me back to my normal size. Oh boy, that's going to be a long walk home. Oh, hi there. Intel fellow Mark Bohr here, still following the seemingly never-ending path of Moore's Law. When I last saw you, I was introducing Intel's 22 nanometer transistor process. But, just like my walk, technology never stops moving ahead. Now, Intel has improved on this design and created a brand new 14 nanometer process. Since I'm already the perfect size, let's take a look at what's changed. Here's a familiar sight, Intel's 32 nanometer planar transistor. As you'll remember, the 22 nanometer process made the jump into the third dimension with its tri-gate transistor design, offering better performance, power, and density. In the last video, we showed a single fin to illustrate this concept for simplicity. But in reality, most 22 nanometer transistors produced today feature not just one, but multiple tri-gate fins, often 3 or 4. To meet the challenges of the 14 nanometer process, the tri-gate fins were once again the main areas of focus. We made them taller, thinner, and spaced closer together. This improved technology provides 3 major benefits. First of all, it is faster, allowing more processing and ultimately better performance. Secondly, the new design requires less active power, contributing to longer battery life and also helping to reduce our carbon footprint. Third, the new 14 nanometer tri-gate fins are so effective that we can get by with fewer of them, requiring even less area per transistor. And taken together, the improvements of this new 14 nanometer design result in an improved user experience that enriches the many parts of our lives touched by technology. You know, it's hard to keep up with the pace of innovation here at Intel, and it's even harder when you're microscopically small. But for now, my walk continues. You know, I wonder if there's a nano bus stop around here somewhere.
Okay, so you saw the modification that was done to handle the current. Okay, again,
All chips start out with a very simple raw material,
just a minute. This
sand.
video
Sand is primarily made up of silicon dioxide or silica. Silicon is the second most abundant element in the Earth's crust, but is only ever found in compound with oxygen. Complex chemical and physical processes are required.
Okay, so miniaturization process is ongoing. Of course, later they talked about the 9 nanometer, then the 6 nanometer. Though I haven't seen any details of how they had done that, but they had done that, and using the same technology, the microelectronic platforms. Okay, because some modifications, of course, but this is happening, and you know, when we started discussing about or learning the concept of single electron transistors, and of course molecular transistors. Okay, because when I was in Sweden, there was a colleague from Pakistan who actually was working with the molecular electronic platforms, and I used to spend some time with him also off and on to understand what is actually happening there, where instead of a solid state transistor, we talk about using just molecules, where you can change the state of the molecule from one cyclic form to another using some form of voltages. Okay, and if you can do that actually very effectively, then we are already at the molecular size transistors. So this curiosity was always there as to how or what next is happening, because the Moore's law will keep on saying that you can keep on adding, because you are saying every 1.5 years the transistors need to be double as per Moore's law. In fact, we have overshoot Moore's law now. That means we are getting it double even in less than 1.5 years. But the idea of the computers, you know, quantum computing coming in, because all these nanomaterials that we are talking about at that size dimension, they actually follow quantum mechanics. Okay, so quantum physics in play, and how to translate that movement of electrons under the, we can say, under the formulae that govern quantum mechanics and trying to integrate that into electronic circuits to come up with the quantum computer is, I'll say, very, very intriguing, very, very complicated. But of course, scientists are working on that day and night. Okay, it's going on. The research is on it. So, I had the opportunity once to go to California. I mean, I was touring the US, and Stanford University actually had invited me to deliver a talk in Stanford University. So I said, okay, since I'm there in the Silicon Valley, nobody can stop me from going over to Intel. And, I just landed up in Intel because I had just 1 day extra. I landed up in Intel and just went and asked to meet Mark Bohr. And they were like, surprised, did you have an appointment? I said, no way, I don't have no appointment. I just walked in. I said, you cannot do that. I mean, it's not possible. He's very busy, he has a lot of other things, a lot of meetings. I said, I need to meet him. I've come all the way from the northeastern part of India, and I need to meet him. And they were like surprised. They said, what is this adamancy? I mean, I said, I have a few questions, and I don't know whom to ask. So I really need to ask because I'm teaching. I'm a professor. I'm teaching, and I really need to get these answers. And they said, okay, you wait. We have to try to see if we can get him, connected. And then finally, they said, okay, he has agreed. So you have to wait. But so he kept me waiting for 1.5 hours almost. And finally, we did meet. Okay, it was an experience, I can never forget. And that's I'll suggest also you people, it's very important that you meet people. You should not be shy. He's fine. When he is at a altogether different level, but what's the harm in trying to meet him and get to know a few things? But anyway, we almost talked for about 15-20 minutes, and then he gave me a very clear understanding within that very short time on what Intel is actually gearing up for quantum computers. And they are, believe me, going very fast. We also talked about molecular electronics, but somehow, Mark Bohr said that, even though they are experimenting, but they still prefer to go solid state rather than, molecules, okay? Molecules are difficult to play with. That's what he told me. But anyway, it was a very good experience I had, and, was just waiting for the thing to happen very soon. When we actually move into quantum computing, quantum computers can be purchased off the shelf. So nanotechnology, can actually or is really playing a big role, and especially in the development of quantum computers, because there's no other way out. And that is not the only thing, because since your FDP is more on quantum computing, I'll try to concentrate on that, but that's not the only thing. Like I told you, any vertical you talk about, say talk about agriculture, you understand what you mean by saying vertical, right? That means any technology developed, it keeps on improving, right? New and new things happening in that particular domain. That means you put science and technology into agriculture and you get better yield, you keep on improving. You find out newer ways, you find improved systems, irrigation and whatnot, and you are improving and you are going up vertically. That is one vertical sector, okay? Then maybe automobiles. You're talking about automobiles, right? You think about our old cars, think about the current cars, a lot of technology, it's going up vertically. Any area you talk about, they're moving up vertically. And then all of a sudden, nanotechnology comes in and just cuts across horizontally. Okay, it's a horizontal technology, and that means it is cutting across all these vertically standing technologies. That means it is making its presence felt in all these technologies. So no matter. Just a minute. Let me quickly take this call. Sorry about that. Actually, it's from my wife, and as told my driver got sort of stuck up with this situation where my uncle and auntie got murdered. So my wife could not take her car. She's not very comfortable driving in the traffic. So she just called saying, somebody's picking me up. Please pick me up on the way. Anyway, so let's see. So, yeah. So what I was talking about, so many different areas that nanotechnology can make an impact. Okay. I would have loved to tell you what's going on here, what we are doing, but I don't really have so much of time. Okay. So I won't go into those, but let me give you a gist. Okay, it's a small thing. See, my background is in electronics, right? You know that already. So basically, I'll say I'm a microelectronic engineer. And then I moved into nanotechnology for my research. And I took a PhD in nanotechnology. And at the time, I realized how research has gone so interdisciplinary. And I was working with so many different people. That passion for research suddenly came up, and I was like very passionate. And I was working with agriculturists, I was working with biotechnologists, microbiologists. Okay, I was working with chemists, I was working with physicists. In fact, I spent a few months in the Assam Bose National Center for Basic Sciences in Kolkata. Okay, just learning physics. Because my physics background not that strong, me being an engineer, and I always sort of thought that the question as to why are we doing things. I used to do that a lot to my supervisor. My PhD guy used to go crazy sometimes. He comes up with an idea, and I say, what's the use of it? Who will use it? And he used to get upset and say, it's not only about using, it's also about knowing, it's about finding out new things. I said, but I'm not interested. Somebody has to use it, right? But anyway, gradually I learned that, the importance of basic science in designing. Because for me at the time, it was roughly, we used to do a lot of things. I used to do alone a lot of things. And then once I see the observations, I used to try to analyze why that happened or how that happened. Rather than initially preparing and saying that I want this, so I will proceed that way, I was not capable of doing it initially as a researcher. And then the time I spent in the Assam Bose Center, that opened up my eyes as to the importance of basic science in any type of applied research. Okay, so all of you are from different domains, and you can actually start thinking of exploring nanotechnology for your research also. You will definitely find something that will match your own interests. Okay, and so the domain of your work will increase as you start collaborating with people. Okay, so I did that a lot, collaborations, and my collaborators are still around with me, and we have done some beautiful work. I'll sometimes share with you all. But one small thing I want to say. What is the time now? It's okay. I'll take another 5 minutes and finish off. Since I am not a material scientist, I was not very keen on thinking of trying too many different materials for the research. Because every time you start working with a new material, you really need to understand the material, the crystal structures, the orientation of the atoms, the work function, band gaps, optical band gaps, so many things. And then, I decided, let me concentrate on the few that I can master. Okay, so I did extensive study with a few semiconductors and a few metals, not many. Okay, and our group is capable of handling this material, for any type of application. So then, of course, we did not want to, just as we are restricting the number of materials, we did not want to restrict our applications. We wanted to do everything. Okay, and that's the wonderful part about nanomaterials, because it's so unexplored. I'll give you one small example with one particular material. It's called zinc oxide. I work extensively with this material, and even if you Google zinc oxide, or you go to Wikipedia and see zinc oxide, you'll find a lot of my publications there, because I started this for a long time and nobody else actually did. And then, from that phase, the typical engineer turned scientist. No, I mean, what was the use? I need applications. I need to use it somewhere. The same zinc oxide material in different configurations, in the different ways of synthesis, we are now using them for sensors, okay? Sensing biological contamination, chemical contamination. We are using them as optical sensors. We are using them to develop solar cells. We are using them to develop self-cleaning clothing. Okay, in fact, our Assamese silk, some of you may know, they're very expensive. We have actually developed a way, we are in the process of patenting it. We've developed a way of keeping it clean all the time. You don't need to wash it. It's self-cleaning, and there will be no fungal growth, there will be no bacterial growth. Again, using that same material. Okay? Then we had made some food quality sensors using that same material. Then what else? I think about 12 or 13 different applications. Oh, sorry, water purification in a big way. Okay, water purification in a big way. In fact, I'll be sharing certain links with Manas, and he can share with all of you. You'll see some of my work even covered by BBC. Okay, and it's on water purification using the same material. Okay, so many possibilities that I find this a very, very interesting, you can say, field of research, and all of you should start thinking about it. And if you feel or you think you can feel free to contact me anytime. If I can help to you, I'm always there. Unfortunately, of course, after joining this university, I'm too much into the management side, being the dean, 2 dean offices I have to handle and 2 director offices. So it's slightly taking my time away from research, but we have developed a center of excellence in nanotechnology at our university here in downtown university. And gradually the group is also becoming bigger and bigger, and a lot of innovations coming out. So I'd love to interact with any of you. If you feel you want to work in this area, I'll be very happy to help you out. So I think, Manas, I'll stop now because I have to move to another meeting. I'm getting calls. So, but I will be happy to take a few questions, if any, at the moment, or you can also put your questions on WhatsApp and send me, if Manas can share my number. So maybe another 5 minutes I can be here, if anybody has any questions.
Yes, sir. So I request the participants to raise some queries, if you have any query. Or later also, if you send to me, so I can send it to sir. That also.
I think that would be a better idea, I guess. So feel free to contact me anytime. Okay.
Sure, sir. Sure.
So I can take leave then. Thank you so much, everyone, for your patient hearing.
So we thank you very much, sir, for your time and such a nice talk.
Thank you so much. So hopefully we'll meet again. All right. All the best for this workshop. Thank you so much. Bye.
Thank you, sir. Thank you.